VLSos here. This is a video lesson on antiderivatives. Quick reminder, two essential projects in calculus, if we are given a function, is to find the derivative, or visually, the slope of a tangent line to a curve. And the second common project is to find the integral, or the area under a curve, often on an interval. We use function notation for a generic function, and the project of finding the derivative is the same in pre-calculus when we called it instantaneous rate of change. The derivative is the rate of change of a function at any point. We can also have a derivative of an entire function and use the derivative of the entire function to calculate the rate of change wherever we wish. In notation, we use prime to mean the derivative. So starting with f, if we were to take the derivative, it would result in finding f prime of x. And this is often the slope of the tangent line. If f were a velocity function, we understand in physics that the rate at which velocity changes is called acceleration. If f were a velocity function, f prime would be the acceleration function. But what about going in the other direction? The inverse of a derivative at the end of pre-calculus we learn to call the integral. But we've studied what the integral means as an area under the curve. Area under the curve is a visual representation of an integral. AUC for area under the curve. And when we calculate the area under the curve of a function, what we're doing is we're taking the sum of change. And if this is confusing, think of having a starting location, and if you knew from the start all of the changes during a journey that were made, you'd be able to use that information to find your final position. The integral of velocity is position. And if an integral is a sum of change, it's like knowing a starting position and knowing by your velocity how that starting position changed and at what rate it changed by. And if you had that information, you'd be able to find your final position. An integral, or an area under the curve, is literally a sum of change. If velocity is the rate of change of the integral. If we've given f to be the symbol or function notation for velocity, it is common to then call the integral the capital letter of that function, in this case capital F. We can be given a position function and take the derivative twice to get to acceleration. If we had a function for acceleration, we could find the area under the curve, find the integral, which would be the sum of change of acceleration, and give us information about velocity. We can integrate again and get position. Because there is this inverse relationship between a derivative and an integral, we could also call an integral an antiderivative. Anti is like the idea of going the opposite way. If we're going down in a hierarchy when we take the derivative, going up in that hierarchy would be the antiderivative. Now, some calculus classes distinguish between an antiderivative and an integral. There is not a whole lot of need to differentiate between the two. Those terms are essentially the same. People that feel there is a difference think of the difference as the antiderivative is just the equation part that you're focused on, and the integral includes the antiderivative and also information about the interval in which you're finding the area under the curve. Concrete example. If we have a function like 3x squared plus 4, then we could find the derivative of that function. We're familiar with the power rule. The first term, bring the 2 in front to multiply the 3, reduce the exponent by 1. And the derivative of this constant 4 is 0. We could ignore it and didn't have to write it. But what about the antiderivative of f? We'll call this capital F of x. The antiderivative of this is x cubed for the first term. And if you're wondering how to do that, go backwards with the power rule. The derivative of x cubed is 3 in front, reduce the exponent to 2. So the antiderivative is going backwards. Let's go backwards with 4x. The antiderivative, we'll go backwards with 4 and get the antiderivative of 4x. If you want to be convinced, then take the derivative of 4x and it reproduces where we started, 4. But there's something else, an unknown constant piece. Where did it come from? Well, think about the relationship here. If we took the antiderivative of 6x, then we would get the antiderivative 3x squared. But we also have another component of this function that disappeared when we took the derivative. So when you go in the opposite direction and take an antiderivative, you create information that you may not know the exact nature of, but it's something in addition to what you started with. Taking a derivative is a process that reduces the amount of information that you have. Taking the antiderivative assumes that there is more information than your starting point, but you don't have or know the exact nature of that information. This is similar to when we talked about having a starting position and knowing your velocity along a trip. If you have a starting position and know how you changed from it, you can determine your final position. The velocity, or the integral of the velocity, is the sum of all that change. But what's unknown, what is required in the final position function, is that unknown starting location that is not captured in just the sum of all the change. We call this unknown that gets created the constant of integration.